All right, guys, let's talk about sequences. If you were in class, you know that this whole topic kind of frustrates me because it's really a copy of stuff we've already done. It's just a slightly different context, a slightly different vocabulary involved. But there's two different types. We have arithmetic, not arithmetic, but arithmetic because it's an adjective, and geometric. The whole difference between these two, it is exactly the same concept as our difference between linear and exponential, okay? So we're focusing on arithmetic today. We'll get to geometric later, but arithmetic is all linear situations. So remember that linear situations have a common difference. So as you look at your data, you're going to see that there is a common number. It would help if I spelled difference right. There's a common number that they are being added or subtracted every single time, okay? When we were talking about exponential problems, we called that an additive rate of change. Remember, versus when it's exponential, you have a multiplicative rate of change. So we're talking about an additive rate of change. Sequences look a little bit different than our normal relationships. A sequence is simply a list of numbers that follows a pattern. So like 1, 3, 5, 7, 9, and then it would keep going. You've done patterns since you were in elementary school. When you very first started out, they might have been colors or whatever. This is an arithmetic sequence because if you notice, every single time we are adding to. Consistently over and over, the rate of change, the rate at which it is changing is by adding to every time. Where sequences get a little bit different than normal linear situations is we typically start with the y-intercept, right? So if I'm thinking about a table of values, we would typically start with the 0 value, okay? And then we would go on from there. When we were doing the real world problems lately, we could start with the initial value. Well, with a sequence, this doesn't count as the 0 value. This is the first number in my term is a 1. The second number of my term is a 3. The third term in my list, I'm saying it wrong. The third number in my list, or the third term, is a 5. The fourth term is a 7. The fifth term is a 9. We don't actually know the 0 term. So what you're going to have to do, if we think about this as a traditional linear situation, the formula would be y equals mx plus b. Okay, my slope in this situation is I am adding 2 for every 1 we go, right? Remember your rise over run, so my slope would be 2x. And then I would have to back up to figure out that y-intercept value. You can back it up right here and say, okay, well, if I back up to the 0 term, in order for me to be able to add 2 and end up at positive 1, I need to subtract 2, and that would tell me, oh, my start value, the way we've typically thought about it, would be a -1. Okay, that's not anything too terribly difficult to do. If you had a table that was missing the y-intercept, you could figure it out. You just kind of have to know, because this isn't labeled as 1, 2, 3, you have to know that sequences start with number 1, not with 0 like we have in the past. Okay, so same concept. The other added part is, and this popped up on the mock test and several people asked me about it, that this is, you can call this your A1, your first term, A sub 2, A sub 3, A sub 4, A sub 5. We name our terms with this notation right here, okay? Well, we're used to going down and saying, well, what would the X be? For whatever reason, because mathematicians like to make things more difficult, we use an N instead of an X. Still is going to function basically the same. So it's saying, okay, we know the second term, the third term, the fourth term, the fifth term. What is the nth term? You'll see that written sometimes. Basically, it's just saying what is any number term, whether we're looking for the 11th term or the 15th term. It's just a way to generalize and say A sub n. Well, if I write a formula to find the nth one, sequences are just slightly different. They say, okay, if I follow my old mx plus b, I'm going to start with a -1, and then every single time I'm adding 2 for every level that I'm on. So if I need to get out to the 4th one, I'm going to start at -1, and then I'm going to add +2, +2, +2, +2. I'm going to do 4 2s right there, okay? It's the same thing. It's your mx plus b. It's just rearranged a little bit. Because for some reason with sequences, we like to see, oh, here's where I started, and then I added 2 every single time. But you notice I even just then started to go, well, that's where I started. That's not what my formula is showing. My formula is backing it up to the 0, which brings us to the other way to write the formula, and that is, let's start the sequence truly where it starts with 1, and I'm adding 2 every time. But because I kind of took this shortcut, this head start value, I've got to do n-1 to say, okay, this isn't really the starting value. I would have to subtract 1 from it, okay? And I know that that doesn't quite make sense, but it will make sense when I do some examples. So what you need to know is you've got 2 versions of the formula. You can say, oh, a sub n equals a sub 0, okay? That's saying the 0 term, that is your 0 term, which is the y-intercept, okay? Because I had to go back to where the 0 value was, plus d times n. D is what we call the common difference, okay? So the common difference, which is also happens to be the slope. So this is your same like mx plus b, just in a slightly different order. Again, it frustrates me. We have to find new ways to name things that we already know. But this is your 0 term, back it up to the y-intercept, and then what are you adding every time? And then just an n instead of an x because it's sequences and we use an n, okay? Well, the other way to do it is to say the formula is a sub 1. So let's go ahead and start with the first term in my list, okay? Rather than backing up to the 0 term, let's actually start with the first term. We're still adding that common difference every time, but then you have to do n-1 because you're not starting at the true start, you're starting at an adjusted start, if that makes sense. And so the d here is still your common difference. All right. So 2 different formulas. I have seen both of these versions pop up on like answer choices on a test. So they're very simple and connected once we see it, but we do have to be familiar with both of them. I wish I could tell you only had to know one, but you don't. So let's do a couple of examples. My first example is 8, 4, 0, -4, -8, ... So the first question is this even an arithmetic sequence? Does it even fit the pattern that we're using here? So yes, it is arithmetic, because if you notice, every single time I'm subtracting 4, subtracting 4, subtracting 4, subtracting 4, it has a common difference of -4. So I'm just going to be lazy and write d equals -4, okay? So now I start writing my formula. I've got 2 different ways to do it. The way that y'all are more familiar with is to say, okay, whatever the nth term, if I want to jump way out here in the future, I can, this is my 1, 2, 3, I can back up to the y-intercept because we're very used to starting with the y-intercept, and I'm totally okay with that. So if I follow my pattern, I need something that I can -4 and it's going to end up at 8. That would be a 12. And then what's happening every time? We're subtracting 4 for every level we go out, okay? Totally makes sense. Y-intercept, slope, same thing. The other method is, if you don't want to figure out the y-intercept, okay, the sequence is actually truly starting at an 8, and then we're subtracting 4, But to make up for the fact that we got a head start, we have to do n minus 1 so that it actually works out and makes up for that change. Now, I get that this is kind of confusing, and those seem like two totally different formulas. Well, let's see what happens to this second formula if I simplify it a little bit. If I distribute that out, I get negative 4n, and let's see, negative 4 times negative 1 would actually make plus 4, and then the 8 out front I just carried down. Then when we combine like terms, we actually end up with 12 minus 4n. So doing that n minus 1 is basically just a way to make up for the fact that you're cheating and not starting with the y-intercept, okay? Both of these are correct. Both of these are good answers. Both of these are answers that you might see in a multiple choice question. All right, one more example. Let's go negative 10, negative 7, negative 4, negative 1, ... So first off, is it even arithmetic? Do we have a common difference happening every time? Well, that one adds 3, then we add 3 again, and then we add 3 again. So yes, it is arithmetic because the common difference is positive 3. You don't have to write the positive, I just do because it helps me write the formula. All right, then for my formulas, I have two options. I can back up to the 0 value. Well, in order to make this work, I would have to start at negative 13. So I could say negative 13 plus the common difference times n. Or if I don't want to do this math over here, basically the second formula looks trickier, but it's actually easier because you don't have to do any math at all. You say, okay, equals, I started at negative 10, I'm adding 3 every time, but I know I cheated because I don't have the 0 for the y-intercept, so I just put n minus 1 makes that adjustment for me, okay? I hope that helps you write these formulas. They're very simple once you get doing a few of them, but they are kind of tricky when you start, so good luck.